Hi, I'm Pushp, Sirohi, double masters in human resource and marketing management, and representing IBM Indians here as an onboarding specialist. And interesting in even behavioral science also works on different aspect of life too, like where do we come from, what are we, where are we going, for which we must aware of cosmology to study the entire universe. So let's introduce cosmology in our life. So cosmology is a study of entire universe, and covering same in a single video may seems like a daydream. But I try my level best. I hope that video will inspire men and women to further explorations in space. So in Wikipedia you'll find out the definition of cosmology. It comes from the word Greek word cosmos means world, and logia is a study. So it means it's a study of world. As a branch of astronomy concerned with the studies of origin and evolutions of the universe from the Big Bang to today on its into the future. It is the scientific study of the origin, evolution, and eventual fate of the universe. Physical cosmology is the scientific study of the universe origin, its large scale structures and dynamics, and its ultimate fate, as well as the law of science that governs these areas. The term cosmology was first used in English in 1656 in Thomas Blant's Glossographia, and in 1731 taken up in Latin by German philosopher Christian Wolff in Cosmologia Generalis. Religion or religious or mythological cosmology is a body of beliefs based on mythological, religious, and satirix literature and traditions of creation myths and astrologies. In easy and to understand concept, cosmology is a study of universe or cosmos, regards as whole. The universe, after all, is richly textured with structures on a vast range of scales: planet, orbit, stars. Stars are collected into galaxies. Galaxies are gravitationally bound into clusters, and even clusters of galaxies are found within larger superclusters. We consider how relatively small objects such as galaxies, clusters, and superclusters are formed as the universe evolves. Just as a cosmetologist try to make a human face more harmonious by soothing over small blemish such as pimples and wrinkles, cosmologists sometimes must smooth over small blemishes such as galaxies, a science which regards entire galaxies as being small objects might seem at first glance very remote from the concerns of humanity. Nevertheless, cosmology deals with questions which are fundamentals to our human conditions. The questions like where do we come from? What are we? Where are we going? Cosmology grapples with these questions by describing the past, explaining the present, and predicting the future of universe. Cosmologists ask questions such as what is the universe made of? What do we come from? What are we? Where are we going? Paul Gauguin said in 1907, Museum of Fine Arts, Boston University, or two more awesome questions like infinite and a spatial extent. Did it have a beginning sometimes in the past? Will it come to an end sometimes in the future? So cosmology deal with distance that are very large, objects that are very big, and time scales that are very long. Cosmologists frequently find that the standard SI units are not convenient for their purpose. The meter M is awkwardly short, the kilogram kg is awkwardly tiny, and the seconds is awkwardly brief. Fortunately, we can adopt the units which have been developed by astronomers for dealing with large distance, masses, and times. Even in ancient time, cosmology was based on observations. Unfortunately, those observations were frequently imperfect and incomplete. Ancient Egyptians, for instance, looked at the desert plain stretch away from the Nile Valley and the blue sky overhead. Based on their observations, they developed a model of the universe in which there is a flat earth. Greek cosmology was based on more precious and sophisticated observations. Ancient Greek astronomers deduced from their observations that the Earth and Moon are sphericals, and that the Sun is much farther from the Earth than the Moon is, and that the distance from the Earth to the stars is much greater than the Earth's diameter. Based on this knowledge, Greek cosmologists devised a two spheres model of the universe in which the spherical Earth is surrounded by a much larger celestial sphere, a spherical shell to which the stars are attached. Between the Earth and the celestial sphere in this model, the Sun, Moon, and planets move on their complicated apparatus of epicycles and deference. Although cosmology is ultimately based on observation, sometimes observation temporarily lag behind theory. During period when data are lacking, cosmologists may adopt a new model for aesthetic or philosophical reasons. For instance, when Copernicus, proposed a new sun-centered model to the universe to replace the Earth-centered two-sphere model of the Greek, he didn't base his model on new observational discoveries. Rather, he believed that putting the Earth in motion around the sun result in conceptually simpler, more appealing model of the universe. Direct observational evidence didn't reveal that the Earth revolves around the Sun, rather than vice versa, until the discovery of aberrations of starlight in the year 1728. Nearly 2 centuries after the death of Copernicus, Foucault didn't demonstrate the rotations of the Earth. Another predictions of the Copernican model until 1851, over 3 centuries after the death of Copernicus. However, although observations sometimes lag behind theory in this way, every cosmological model that is eventually supported by observational evidence must remain pure speculation. The current standard model for the universe is Big Bang, the Big Bang theory model, which states that the universe has expanded from an initially hot and dense state to its currently relatively cool and tenuous state. And the expansion is still going on today. So the whole world, understand in two ways about cosmology. Of one way is the way of Newton, so the Big Bang theory divided into two, two ways. Like first is the way of Newton, and another one is the way of Einstein. So Newton said mass tells gravity how to exert a force. Force tells mass how to accelerate. And the way of Einstein, mass energy tells space, time how to curve. Curved space-time tells mass energy how to move. So for better understanding, we must understand Newton versus Einstein on cosmological scales. The dominant force determining the evolution of the universe is gravity. The weak and strong nuclear force are short range forces. Both gravity and electromagnetism are long range forces. On small scales, gravity is negligible, small compared to electromagnetic forces. For instance, the electrostatic repulsion between a pair of protons is largely by a factor than the gravitational attraction between them. However, on larger scales, the universe is electrically neutral. So there are no electrostatic forces on large scale. Moreover, intergalactic magnetic fields are sufficiently small that magnetic forces are also negligible, tiny on cosmological scale. Ironically, then gravity, the weakest of all forces, form from a particle physical standpoint is the force that which determines the evolution of the universe on large scale. Note that the in referring to gravity as a force, I am implicitly adopting a Newtonian viewpoint. In physics, there are two useful ways of looking at gravity: the Newtonians or classical viewpoint, at the Einsteinian or general relativity viewpoint. In Isaac Newton's view, as formulated by his law of motion and law of gravity, gravity is a force which causes massive bodies to be accelerated. By contrast, in Einstein's view, gravity is manifestations of the curvature of space-time. Although Newton's view and Einstein's view are conceptually very different, in most cosmological contexts they yield the same predictions. The Newtonians' predictions differ significantly from the predictions of general relativity only in the limit of deep potential minima, to use Newtonian language, or strong spatials. In these limits, generally relatively yields the correct results. In the limits of shallow potentials minima and weak spatial curvature, it is permissible to switch back and forth between a Newtonians and a general relativity relativistic viewpoints, adopting whichever one is more convenient. So mostly I will frequently adopt a Newtonian view of gravity. So in many contexts, like it is mathematical simpler and conceptually more familiar. So that's about cosmology, guys. I hope you like it. Thank you and have a nice day.